welcome everyone to today's Dig Deeper webinar. It's an exciting webinar for today. The topic is climate change induced risks for the performance of vegetation on mine rehabilitation soil covers in Latrobe Valley. And I will be saying a few words of introduction in a moment to introduce the speakers today. But I'd also just like to begin by acknowledging the traditional custodians across all the lands on which we live and work. For me, right here in Brisbane, that's the Jagera and Turrbal people, and extend that to all the lands on which we meet today across the country. So I would like to just mention a couple of things before we get started. Number one is that we are recording today, so please take note that we are recording today. That's been very important, so that people who cannot make it today can. The others can listen to it later offline, and we've been getting very good numbers. Lots of people tuning into the webinars, so it's very exciting actually on the YouTube channel. Also wanted to mention that if you do have questions or comments which come up throughout the presentations, please do put them into the chat, and then what we'll do is we'll call them out and we'll at the time for questions, and we'll get into the Q&A after the speakers have spoken. So what I'll do now is I'd just like to introduce the speakers, starting with Professor Thomas Baumgartl, who you can see here on the left-hand side of the slide. So Thomas is the director for the Future Regions Research Centre at Federation University and has been very involved in CRC time for several years now. It's a great pleasure to be hearing from Thomas today, and also a great pleasure to be hearing from Vilim as well, Filipović, who was actually previously at Federation University but is now at University of Queensland, which is actually where you used to be, isn't it, Thomas? So almost like a little bit of a swap. That's quite interesting, isn't it? Anyway, very great welcome to Vilim, who's here as a lecturer in the Soil Science School of Agriculture and Food Sustainability at the University of Queensland. So it's excellent topic, excellent speakers. I will, without any further comments, hand over to you, Thomas, to get us started for the presentation today.
Thank you, Tom, for the introduction, and hello, everyone. I'm talking today from the land of the Gunai people, and as you introduced the topic, we are talking about a project which is related to the region, but also has potential to spread further and inform other similar questions. Before we go into the very detail, which is being presented by Vilim, I'd like to give a bit of a background, because not everyone knows probably the conditions of the Latrobe Valley and the mining activities here. As you can see from that map, Latrobe Valley is in the east of Melbourne, about 200 kilometers east. The coal mines there they exist for partly more than 100 years, and they have been created to be linked to power stations and provide the majority of electricity to the state of Victoria. As we all know, coal mining is coming to an end, and likewise, it's coming to an end in the Latrobe Valley as well. So the operational interest in mining is now being superseded by mine closure and everything which is linked to that. One of the mines, Hazelwood mine, is already closed since 2017. And the other two mines, Yallourn and Loyang, which you can see in that map below, and I probably can show that laser pointer. Yes, here. They're going to close in 2028 or 2035, respectively. What is very interesting about the mines is that coal is really accessible and plentiful in the region. The coal seams are quite deep, up to 100 meters, and the brown coal seams are mined down to a depth of 150 and 200 meters. There are only very narrow interseams, and the stripping ratio is up to 5:1, so quite very different to many other regions in Australia or worldwide. The Gippsland, or the Latrobe Valley, actually provides about 25% of the global resources of brown coal. So it's really a major resource for the region. Mining, although it's such a rich environment for coal, it does come with its challenges as well, like probably every mining activity. One of them is the stability of the excavated pit, so the batter stability. And there has been an incident in 2007 where a batter has failed. The failure of the batter was a result of a feature within the coal, which is vertical cracks or joints, which allowed water to infiltrate, and that under very wet and long ongoing rainfall conditions. And the mechanical stability was challenged by that water, which was infilling those cracks, and hydrostatic stresses were pushing a block of coal, as you can see at the top slide, was moving that away, and caused quite serious issues. The other incident and risk which is associated to coal is fire. The coal as such has a high potential and risk for self-igniting, so spontaneous combustion is a problem. The Hazelwood mine fire, however, in 2014, it's quite confirmed that it was caused by amber, which was flying in from a bushfire and starting the coal to ignite, and that fire was ongoing for 6 to 7 weeks, as far as I remember. So the mine closure, which is envisaged or currently taking place, needs, for this specific environment, needs to consider certain of those challenges which I've just mentioned. That is the better stability, the fire safety, but also to what extent is the coal actually long-term stable. So wetting and drying can cause shrinkage of the coal, and with the shrinkage goes along a compartmentalization of the coal into structured coal, which has very different stability parameters. Likewise, we did some study around the influence of different pore water qualities, how they may influence the mechanical stability, and there are, depending on the type of salt which is being considered, there are either beneficial or negative effects in terms of the stability. And the fact that the pits do have quite steep slopes, so quite an incline in the batter, that question can be quite of relevance. The cover, therefore, needs to take all this into account, and designing an appropriate cover is also the way forward, how one can control those challenges. So the cover is really an integral component to build a stable landform into the future. In all the discussion around how mine closure can look like, there's also a regional component. So the communities have certain interests, and I would just briefly highlight the question whether those pits will be filled with water, which has some benefits from a stability point of view, or they remain empty. And there's a lot of discussion and a lot of reasons connected to that, why the one is superior, the one solution is superior to the other solution. But it's an ongoing process. Nevertheless, whatever is going to be done, the coal needs to be covered. And that is quite different to many other parts in mining, where we are usually covering the waste material, but not the resource. And the coal as a resource, as an organic rock, has its own challenges. Now, when we look into covers more specifically, what are the functions a cover has to fulfill? There's, on the one hand, it needs to control infiltration. It needs to be able to absorb water, but it also needs to prevent excessive runoff. It's usually being used as a substrate for plant growth or for ground cover. It needs to be of a condition that erosion is avoided or at least minimized. The cover itself, in many cases, should minimize deep drainage, and in the case of coal, it is also a tool or measure to minimize or avoid the risk of fire. Now, in discussions around those functions of covers, the question has come up to what extent climate change and therefore the vegetation cover and the types of vegetation we can find on a cover, how climate change may have an impact on the performance of such cover. And climate change, in the case of Gippsland, is being forecast to create more dry conditions, interspersed probably also with severe droughts, as it has happened in the past, and linked to less rainfall events, but rainfall events with higher intensity. So the question is, how does the current cover design and the vegetation cover, which is part of the strategy to make that cover functional, how does climate change may influence the surface stability? So our project is going to investigate those covers and their suitability to ensure a long-term strategy building a stable landform. The research process out of that is that we created a cover trial and designed it as a column study with the objective to understand the hydrological performance and response of the hydrology for typical substrates as we can find them in the region. One of the objectives was the prediction of hydrological performance through numerical modeling and determination and fitting of hydrological parameters, with the goal and the outcome that we are understanding the performance of the cover and can make prediction using representative substrates. A second outcome was also that this will help us to suggest a cover design for field conditions and as a long-term trial. The project was funded together with the CRC Time, but primarily by the Victorian government, by the back then Department of Jobs, Precincts and Regions, and here the group of the Earth Resources Policy and Programs. And with that, I'll hand over to Vilim.
Thank you, Thomas, and thanks, Tom, for the nice introduction. I will present more specific results of our study. So I was able to help with Thomas to join the Thomas's team in Latrobe Valley through this CSI Time project, and my specific interest was doing the soil column experiment and also numerical experiment. So how we performed that I will present a bit of methodology and then some of the results we found. So we conducted a control column experiment using the coal, clay, topsoil, and vegetation cover from Loyang. So before doing that, we also did initial numerical modeling, which helped us determine the final design of whole system. So for that, which was kind of in our sense new and specific, we tried to conduct the column experiment to be as close as possible to the field conditions. So you can see here on the picture how we did that. So we actually used undisturbed soil column slabs. So they were cut to fit the soil columns. And we were also very careful to prevent any bypass flow along the side of the walls of the columns. In the second step, we added clay material, which was left in aggregated state as you would find it in the field. And on top, we put a layer of topsoil with already well-developed root zone. So we were thinking whether to apply seeds and grow the plants from the start, but in our sense, it was more important to have uniform soil cover with already developed root zone, because we wanted to see what effect will the drought have on plants as well. So we kind of cut down the undisturbed topsoil layer together with the plants, and that was done on Loyang mine site. So to be again as close as possible for what is present in the real scenario. The column experiment had two scenarios, which actually differ in soil cover depth. So we put S1 scenario with 40 centimeters of soil cover and S2 scenario with 90 centimeters of soil cover. So very large differences between the two scenarios, just to capture this effect and to kind of pronounce the effect of hydrological behavior. And we also have two types of grasses at the top. One was dominated with cocksfoot and other with ryegrass. Beside measuring, so we measured meteorological parameter. Even the whole column experiment was inside of the glass house. We applied irrigation at the beginning to stabilize the whole system, and then we started the drought scenario. We included some sensors to measure water content and matrix potential measurements. Actually, it was more than 20 sensors, so very highly censored columns. And we also measure column weights and outflow drainage. So that was all recorded. So you can see here on the picture how the experiment looked like. So we had also, we had three repetitions in each scenario. So you can see two types of vegetation and two types of depth of the soil cover. So altogether 12 columns. And you can see here also the placement of water potential sensors and also placement of water content sensor. And that was done together with initial modeling to get a feel where to put the sensors. And also we had some sensors installed in coal material itself. So that is how it looks. And you can see also the drainage collection boxes, and also this structure, metal structure, is for weighing the columns. So they were weighed on regular basis. In terms of laboratory trials, we had additional experiment which help us get some hydraulic properties and water retention properties. So we use this HyProp system and VP4C devices which measure the water retention properties, so water retention curve, but also coal retention properties using the soil cores. And basically you put the material under saturation and you conduct an evaporation experiment. This was the fitting of these parameters was performed using Wangen-Uchten model, the classical model, and in the next step, of course, we use that information to do numerical modeling. So in the literature review, we also kind of evaluated which model and which kind of packages, softwares were the most applicable for our studies. So we decided to use Hydrus 1D because the ability of the modeling all the processes we need to model. So we at the end had 3 scenarios. So we had single porosity modeling using laboratory determined soil hydraulic properties, which I showed on the picture before. We did inverse single porosity modeling based on the water content data in the next step, and in the last step we did inverse dual porosity modeling based on the water outflow. And here you can see that we of course very precisely replicated the material distribution which was in the soil columns. We also did examination of root water uptake parameters, so density and depth. And also we put some observation notes corresponding to the soil sensors. So for the first results, here you can see water retention curves measured for topsoil, A, B for clay, and C for coal. And here you can see the table with parameters. So topsoil and clay material has relatively similar properties. You can see that hydraulic conductivity was around 77 at topsoil and double that in clay core. However, what is not noticeable that you can see here that the whole coal material has much different properties. So it has much higher saturated water content, so the amount of water which can hold because of the pore distribution, but also have very, very limited hydraulic conductivity. So very large gradient between the soil and the coal material itself. And of course, given that, the bulk density is also very different. So what we noticed that the parameters were indicating large water retention capacity, but also low drainage of coal, which is the result of pore size distribution. In the next step, after setting up the experiment, this is part of the experiment which showed the most data. So we conducted experiment for much longer. Some of the experiment phase is still going on. So this is just to show the differences and what we recorded in 3 months, starting from March to June. So you can see here 2 scenarios. So you have S1 versus S2 with first type of vegetation, which is cocksfoot, and the second down you can see again S1 versus S2, so different depth with perennial ryegrass. The plants itself, because they are very similar grasses, they didn't have that much effect that the differences would be noticed between those 2 types of plants. However, of course, the difference in depth of soil columns and cover material was very significant. So you can see here for the first layer, so you can see here one of the columns has a dotted line, the other is full line, so you can see the differences. And what is noticeable that the deeper soil soil content measurement, which was very much still very saturated or close to saturation even after the cease of saturation. So that was in the deeper column. And in the lower column, which was 40 centimeters, of course, the drying process start quite sooner. So the larger soil color can store more water for a longer periods of time, and of course that provided wetter conditions on top of the coal, preventing the coal drying itself, and also prevented better response for vegetation. So Thomas will present a very interesting result in root distribution. So it can be seen that the roots are taking up the water on top of the coal itself. Vegetation response was similar, and we were very surprised to see that vegetation was still green after a few months without irrigation, which was a bit unexpected, to be honest. In the second stage, we did perform a numerical modeling. So here you can see the numerical modeling results. So measured and simulated water content in S1 and S2 scenario. So the model was quite good after initially starting with soil hydraulic properties measured in the lab. We did inverse modeling based on the water content data. And you can see, just looking at statistical parameter, the R square was very high, 0.87 and 0.94 with low root mean square errors. So that was quite good. However, that was using single porosity model. And you can see here on the bottom pictures that drainage amount couldn't be simulated with that. What we noticed during the experimental design, that some of the columns show very high conductivity of water. So you would irrigate the water and very fast the coal would just, we noticed just some drainage at the bottom. So after being at the field, we noticed that there are some fractures and cracks inside of the coals. And we kind of expected that this would happen. So it is really difficult to simulate that with single porosity model, where you need to, with single set of parameters, account for matrix flow and for preferential flow. So in the next step, we apply dual permeability model, dual porosity model, which can kind of distinguish between two domains. So it uses two sets of equation, Van Genuchten equations, which tells you, and there are some factors that tells you, one is telling you how the water is behaving in the matrix domain, and the other model is telling you how it's behaving in the fracture domain. So you can see that this dual permeability model simulated quite well. This was the drainage amount with very high accuracy of 0.99, so very good. And that was kind of interesting to see. So soil water content was well fitted using the single porosity with optimized soil hydraulic properties. However, drainage flux was only correctly simulated after using this more complex model. And just to conclude this part, there will be some publications, some milestones are already published with more interesting results and with more findings. Regarding our presentation here and most interesting findings, so what we found that the largest soil cover S2 scenario had the largest water storage, prevent cold drying at the time of the analysis, which is still going. What we noticed, there was a shift from drainage flux to evapotranspiration dominated processes when the drought is introduced. So that means there is a change in how hydrological processes are occurring. So it's very important to have quite good understanding in the sense of climate change, where we expect very large shift between the large drought and also large extreme events in terms of rainfall. Plants show resilience to drought condition, which is of course important for mine rehabilitation. And the larger cumulative outflows are indicating preferential flow and bypassing of water. So that has a large impact on water balance, but also flux dynamics, and in some cases solid transport where there might be some soils that might be important from the aspect of groundwater protection. And at the end, just to conclude, in terms of numerical modeling, it's really important in such cases to do the proper modeling and to apply more complex dual domain models, which are able to explain such processes in more correct way, and also to do proper experimental evaluation of the parameters needed for that process. So with that, I will give back it to Thomas.
Thank you, Vilim. Yes, as Vilim already mentioned, part of the project is to be also destructive, that is to look at the columns posts finishing the study, and we started now to cut up some of the columns to have a closer look at the root distribution. And a big thank you to Marta Kushelkova, who is currently staying with us as an intern student, and she's having the pleasure to investigate the root distribution. You can see a cut through that column in that photo, and hopefully you can make sense out of it. So the top 10 centimeters is the grass, which has been placed onto the clay column or the clay layer at the beginning of the experiment. And then we have about 30 or 25 centimeters of a clay layer, and underneath the coal, which fitted quite snugly into that cylinder. Because we used a grown and well-developed grass topsoil, as you can see with the root mass, that is quite high in the first 10 centimeters, which reflects that root density from the applied grass layer which we put on. Then we have quite low biomass values, and however, when we are getting to that interface from the clay layer to the coal, we find biomass of roots which is actually much higher than even in the topsoil. I hope I can do that. Yes, in that circled, the circled part of that photo shows that interface from clay to coal, and what we lifted up was that layer of roots. So what has happened is that the roots, when they discovered, or when they were getting into struggle to take up water out of the clay layer, they seem to have ground down to explore further water resources to the coal, but couldn't enter the coal because the coal is mechanically too dense. It's impossible for the plant root to really penetrate coal. So they were spreading on the surface of the coal and taking up water based on the hydraulic conductivity and the supply which is possible from the coal. And just from some recent analysis of data, and it's just first analysis, that's why I'm just verbalizing that, there is probably a cutoff between how much water the roots can still take up out of the coal and how much water can actually flow from the coal to that interface. What is or where we are not very clear yet is to what extent the roots can actually further dry the coal. And as I mentioned previously, despite the fact that coal has a total pore water content and porosity of up to 70%, and it hasn't lost a lot of water so far to those water potentials which we have measured. But at some point, it may get that dry that it will start to shrink. and that would allow the roots to go into those shrinkage cracks, but it would also mean that the coal at that point would change its mechanical properties and become less stable. So this is an area of study which is quite interesting, I think, and may have some implications for the design of the covers. A few words about the project life cycle and the next steps for the project. The end of project has been extended to February 2024, and the main reason was that the grass didn't actually die as early as we were expecting. So we stopped watering of the grass in beginning of April, and over half a year we can still see some green grass. So there's still a bit of water uptake, although we haven't provided any additional water to the columns. We are planning for a second phase, and the initial project was designed with the idea that there was going to be a second phase in the discussion with the government, and that would mean to actually upscale that to go into the field and have a field trial. And we know that there's some interest in the Latrobe Valley, but it would be also good to have some interested partners outside the Latrobe Valley. So if there is anyone who from industry or researchers who like to be involved in that, please contact us. And some of the open questions which we would like to explore further is around the rooting depth. So how far can herbaceous plants grow? We, in our example, at 40 centimeters, the plant roots have really spread laterally. That means there's still potential for them to go deeper if they could. If we are thinking of covers, and in the very long term, if we are thinking of woody species, and if woody species are unavoidable, what is their specific rooting depth? Would they behave in a similar way? Woody species roots are probably they will be stronger, even though they couldn't crack the coal, but they could potentially reduce the water potential further than what grasses can do. In the context here, what does it mean if roots are actually sitting on top of the coal? What is happening if there is a bushfire going through a rehabilitated environment, and if roots are actually, depending on the heat and the conditions, of course, would allow a smoldering and a progressive movement of glow to depth? Would there be a risk of ignition of coal through that process? And as a last of possible questions in this list, can numerical modeling be used to predict the behavior of root growth and incorporate that, and by that improve the cover design which we want to achieve as an optimal long-term system? Yes, and that's the end. Thank you.
Thank you, Thomas and Vilim. So we have a few questions. I'm going to just look in the chat here. We'll start with the first one. So the first question from Melissa Salt was, I note that the clay cover has a higher KSAT than the topsoil. Given topsoil is typically sandier than clay soil, what was the cause of this difference?
Yeah, I can take over. At the site, so we decided to design our experiment to be as close as possible to the site. So we used the clay material they often use for their rehab, and they had some rehab trials, and we conducted there this sampling campaign where we took the soil covers. And actually, I was surprised as well that but it seems that the topsoil is a bit compacted, more than it should have been, and it has larger root mass, which I thought it would help with hydraulic conductivity, but it made it quite differently. So it's actually a site-specific just a site-specific parameters that will like that. I don't know if there is an influence also of cattle grazing on top of that, because they have a cattle grazing on top of that surface as well. So there might be some compaction as well due to that. But the most interesting part, of course, it was the coal and soil interface. So even if we could easily adapt the model by presenting some scenarios in which we put more permeable material on top, but the result would be quite the same. So we are interested, like Thomas said, I think we need to explore more of this soil-coal interface. And when we go to the field scale, of course, then you have also the effects of slope. So we want to explore that as well in the next phase of the experiment. So there is additional hydrological effect of potential surface runoff as well, which we need to take into account. Unfortunately, that's not so easy in column experiments.
What I might do with the questions is skip ahead, because I think it's a little bit leading on from that discussion. The last question from Thomas Neem: would not the plant roots, herbaceous or woody, pursue open fractures within the coal, those fractures that provide the secondary permeability in the coal?
That's a good question, thanks. There is a theory and understanding that the roots can open cracks by creating a shrinkage or by forcing a shrinkage of that material. And that is happening because they are extracting water, they are reducing the water potential or increasing the matrix potential, which is creating higher tensile stresses. And by that, they can start to open and elongate a crack and encourage a further crack in development. And while the crack is opening, the root would then immediately go, of course, into that crack, and that would be a continuous process. The coal needs to be quite dry. The water retention curve, which Vilim showed, shows that at the permanent wilting point, which is a 15,000 hectopascal water, minus 15,000 hectopascal water potential, the coal has only lost about 10% of water to that point, or 10 to 15. So that is not a lot of water, but it means from the other parameter values which are connected to it, which is the unsaturated hydraulic conductivity, that the unsaturated hydraulic conductivity at that point will be so low that there's not much water can actually be transported through the coal. So it will be interesting to see if there is a more balance or a stronger development of that root mat over periods of time. And we just had one or half a season, so to say, for the roots to grow and develop, whether they can actually build up such a strong suction that that the coal can be dried that much that the coal would crack. But the roots as such, they couldn't. I don't believe they couldn't move into the coal, because we needed to drill with a drill bit into the coal to install the tensiometers to measure the hydraulic properties. So it's not something which you can just scratch out.
Okay. So look, what we might do then is go back a little bit, and there's a series of questions around what's coming next. Although we have a question on the finding that plants showed resistance to drought conditions, with a specific question on do cocksfoot and ryegrass exemplify typical species used in rehabilitation at the mine?
Yeah, I think that was again a result of specific condition. I think they wanted to, the idea at Loyang was that to do the rehabilitation of the covers in a way that it would be sustainable, and in that sense they put pasture plants. So the idea would have was been to have a, and I think Thomas can correct me, but I think there is some grazing going on part of the slopes. So the idea was to introduce some sort of mixture. So it's a mixture of plants. There are a couple of other plants also inside of the mixtures, like clovers, but we couldn't at that small scale, we couldn't introduce them all, or there were in very small quantities. But the whole mixture is like that is more drought resilient. So they put the mixture there, and the farmers use it not only on the mine side. The farmers using in the grazing country around to be able to be sure that the plants will survive for a longer period of time and that the cattle has enough food. So that was the idea, kind of a combination of having the maintenance of the covers done by animals, and which in turns it's a positive effect and brings everything together more easily. So that was the idea at that particular mine.
Okay. So I'm just kind of working through the questions in the water, which makes most sense to me at the time, not necessarily the water they come in, but we have a question from Nevenka Bulovic, which is, do you incorporate increases in temperature in your drought conditions, or is it only a rainfall deficit?
No.
Yeah, you can answer.
Sorry, Thomas. Yeah, it was a good question, but we had we measured quite precisely the temperature, and we didn't show that. We had even temperature sensor inside of the columns. So for now, we had quite a large variation. You can imagine the greenhouse in Latrobe Valley during the summer and winter. So the gradient was very high. So we had very low and then very high temperature. But no, we didn't do the controlled temperature conditions. So it was just a rainfall deficit. So at the same point, we just stopped the irrigation and just did the drought condition experiment. So, and the temperature was just occurring as naturally occurring in surroundings. So you could see that the greenhouse at the beginning was even open, and then after we close it and protect it from the elements at the end.
I just add there that it is indeed a good question, because there's and that will be of relevance when we have a chance to upscale that onto field conditions. That is the exposition of the slopes. The slopes are relatively steep, so during certain, and if the exposition is towards towards the north, there will be, during summertime and during drought conditions, during heat waves, I would expect that the drought will, that the temperature will have a major impact on the state of the vegetation which is growing there. So if the soil has dried already and there's not such good delivery of water for evaporation and for cooling, then the exposition to the north will really create quite, I think, peak temperatures which are harming, or which can harm the vegetation.
Thanks, Thomas. So, and thanks, Vilim. So we we're getting close to time now, but I'd just like to roll a couple of questions together. So one is a question on what are the next steps for this research? And related to that is a sort of question around, is the plan now to scale up and conduct field trials and use native species? So I guess you can take these questions together. One is particularly around whether it's field trials and the type of species, and another one is more broadly, what are the next steps?
Yeah, I think we have more or less answered those questions already in the discussion, but also in the presentation that just have been asked prior to the finish of the presentation. The idea is to upscale. The idea is to go into the field and have a field scale trial. And as I said, it would be great if we could find some other interested parties that would help the CRC to support this easier. So if there's anyone out there who is interested in that research, we would be more than welcome to have a discussion with you. The other question was future and the next steps, yeah, other species. Do you want to answer that, Vilim?
Yeah, I think that will also depend on the future outcome, and if we find some potential collaboration outside of Latrobe Valley, that will of course change the vegetation, which will. So if we do the experiment in Queensland, of course that will change the vegetation type on top of the cover. It has to. So yeah, we are, and that would be really cool and interesting to look to have different climatic conditions, but also different species, and especially the native species, which are kind of well developed for the conditions.
Well, on that note, what we might do is we wrap up the webinar. I'm going to mention a couple of things afterwards, so please stay on for a few minutes more. But I would like to thank both the speakers. Thank you, Thomas. Thank you, Vilim. Excellent presentation and very, very interesting, exciting work. So thank you. Please do take note that we have another webinar coming up. It will actually be the report launch. So we're doing the report launch for a very interesting report coming up, enabling mine closure and transitions, opportunities for Australian industry. So this is a very exciting piece of work. Another exciting piece of work. We have so many exciting projects. This one is looking at a piece of work tied to a report which we're launching, enabling closure transitions, and so opportunities for Australian industry. And you can see here we have the link on the right-hand side if you'd like to register for that upcoming webinar. And you can see there. Do we have the date there? Is that 20th of November? Is that what it is? So we have the date coming up for that webinar coming up later this month. Please join me in thanking Thomas and Vilim, and we look forward to seeing you at the next webinar.
Thanks very much.
Thank you, Tom. Thanks, everybody.
Thanks, everyone.